Hi, everybody. Uh, Today we'll talk about our two recent articles on Gaussian multiplicative chaos and gluing problem. So, using the framework of random conformal weldings, we have the following two works. First, we studied uh, the inverse of Gaussian multiplicative chaos, which we will define shortly. We studied its moments and some decoupling. And then using those properties and the framework by uh, random conformal welding, or for short, we will say EDGKS, we proved the welding problem. So we'll go over the definition of GMC and its inverse. We'll state the main welding result and some of the main steps and the development they triggered in GMC. Okay, so first we start with defining the Gaussian free field on the real line. It's a distributional Gaussian process with logarithmic correlation. Here we see that when t is s equal to s, this is undefined. So this is not a function valued process. Uh, and so the way around it is is to truncate. So we consider the following truncation. So uh, when t is equal to s, we get log delta over epsilon. And when they're far up, so when we have some t over here, and then it's at least distance away s, then we have that u delta t will be independent of u delta s, right? Because they have zero correlation and they're Gaussian. Uh, for each parameter gamma and epsilon positive, we define a sequence of measures with the exponential weak power so that it normalizes to 1 and the expectation of these measures is Lebesgue. One can show that this sequence is an L2 Cauchy sequence, and so it has a L2 limit, I delta I, which belongs to the family of Gaussian multiplicative chaos. This name originates from Paul Lévy, who suggested to Jean-Pierre Kahn to construct a multiplicative theory similar to the additive one. So, meaning we start with any partition Tk, we could split the field U into a sum of independent Gaussian fields, and then the measured eta can be written as this uh, product. So now we study a product of random variables. Okay, so the measure eta evaluated over the interval 0x, similar to a Cantor-Devil staircase. It's strictly increasing and it has a well-defined unique inverse. So yeah, so let me write like this. And so this is the core object that we will study. Okay. Um, Everything above can be done also in the periodic domain. So where we identify 0 and 1, but we will keep the same notation for this talk. Next, we go over the setup for our main welding result. So just as a reminder, if we start with a homeomorphism between the unit circle, this is called the conformal welding. If it satisfies the following identity for some conformal maps inside and outside the unit circle. Okay. The idea being that you have a sphere with conformal structure given by these two charts, and uh, the boundary. So the sphere is formed out of two disks whose boundaries are identified using this homeomorphism phi. Okay, so this is the identification here. And now we're going to look at the specific case for GMC. So we start with two independent copies of the Gaussian field and construct the corresponding GMC measures with possibly different parameters, gamma 1, gamma 2. Then what we want is we want to, again, we have two disks, and we want to identify a point x1 with a point x2 when their its normalized lengths, GMC lengths, are equal. Okay. So in the language of conformal weldings, we have a homeomorphism map H1 inverse H2x, where H1 is the inverse of the normalized map. So QKX eta 01 is the inverse of the normalized map, right? So QK eta of y over eta 1 is equal to y. The picture is that we have these two disks, and we glue them based on the normalized quantum length. Okay, and yeah, so we obtain some loop in the sphere that has some very interesting properties. So our welding result is that for every pair gamma 1, gamma 2, less than a number that can certainly be optimized, the welding problem for this homeomorphism has a unique solution. So we have two conformal maps, F0 and F infinity, and a resulting Jordan curve that glues these two disks, and it's unique up to a Mobius map of the Riemann sphere. So Peter Jones conjectured that this gluing process with the independent GMCs will produce a random loop gamma that locally looks like SLE. So that's from Loebner evolution. In the 2009 work of by AGKS, random conformal weldings, they, along with Jones, they built a framework for Beltrami towards answering this question. And in the 2010 work, Scott Sheffield found a beautiful coupling of SLE curves in the logarithmic Gaussian field in 2D that allowed him to concretely build this conformal welding. I should mention that it still remains using the Beltrami approach to obtain a parallel proof to the existing ones that this loop gamma is in fact an SLE loop. So there's some proofs using the Sheffield welding. They managed to prove that one obtains an SLE loop, but it's open using this Beltrami approach. Next, we go over some of the main steps of the proof. So yeah, we start with homeomorphism maps involving the inverses, the normalized inverses for each copy. Uh, we extend these inside and outside the unit circle using an extension called the Akfors-Belling extension. Uh, so this extension has corresponding dilatations K1, K2, and Beltrami coefficients mu1, mu2. And finally, we consider the Beltrami equation problem, where the Beltrami coefficient is mu1 inside the unit circle and mu2 outside. Okay, so we have each copy from each side. Then the bistyole factorization uniqueness for Beltrami, we have that the solution F is equal to F0 recomposed with psi1 inside the unit circle and F infinity recomposed with psi2, the extension of the second copy outside the unit circle. And so we indeed get the identity we discussed. So we have two conformal charts, and the boundaries are identified using the normalized GMC map, the inverse normalized maps. So roughly in the EduQS work, um, so as noted there, uh, they roughly study this ratio of GMCs, and which basically quantifies how quasi-symmetric the maps are. And as recognized there, the dilatation diverges as we approach the boundary. And so we are really in the degenerate setting of Beltrami coefficient equal to 1. Okay, so we are away from the usual elliptic setting that we have solutions for Beltrami. Fortunately, there's a lot of literature for studying those degenerate equations. First, we have the work by Astala, so elliptic partial differential equations, and then the Beltrami equation and geometric approach, where they study more general modulus estimates. Again, in the spirit of the Leto estimate. So next we go over some of the key steps in obtaining eccentricities on this Beltrami. We talk about the Leto integral and then what we had to do about the moments, the multiple moments, decoupling, and finally the single point moments. So as a reminder, just as a new thing, starting with some dilatation, Kf, we have the following Leto integral, which is very reminiscent of the Dini integral in ODEs. So we have 1 over average of the dilatation. Let to prove the following estimate for the modulus image of a topological annulus A. So namely the modulus of the, so we start with some annulus, some topological annulus A, and we map it to some other topological annulus, and then the length, the extremal length, the modulus of this topological annulus can be lower bounded by 2 pi, the Leto integral, using an argument principle. Um, This estimate translates into controlling the inner diameter of this uh, topological image annulus in terms of the letter integral, right? So we have this r, little r, and big R. Getting mapped to this. And so if one can prove that the letter integral diverges as r goes to 0, uh, this upper bound will go to 0. And so the this inner diameter will go to 0. And so we have good control for points. We have good control for points in inside that annulus. Okay, so the letter theorem. Um, so he proved that if the Beltrami coefficient is measurable and compactly supported with mu z is less than 1 for almost every z, the distortion function being locally integrable and a letter condition, uh, as mentioned above, showing that this diverges as r goes to 0. Then one obtains that the degenerate Beltrami equation has a homeomorphic solution in W11 in Sobolev. So the main idea of the proof of Leto is to approximate by the elliptic solution. So now these guys have L infinity norm strictly less than 1. And and then by getting uh, showing that the letter integral diverges, uh, one gets an equicontinuity for the corresponding solutions. Okay, so we get some equicontinuity for all these maps. So we get a subsequential limit for the uh, uh, limiting L equal to infinity solution, which is the one we want, the degenerate case. Okay. So uh, in the case of independent copies, we had to look at a modification of the letter integral and theorem. So we started with the following estimates. So we have, again, um, an annulus and its image given by some homeomorphism F. But now this homeomorphism has separate dilatations on the upper and lower half plane, similar to having different Beltrami coefficients inside and outside the unit circle. And so we proved the following Beltrami estimate. So for this particular case, we have the following modification. So so before we had that this is bigger than 2 pi LKF, right? Now we have 2 pi. So let me remind you. So LK was 1 over integral K. Here we had to slightly modify so that we have an integral for each annulus. So we have an annulus A that we split into two parts, A plus A minus, and we integrate separately. The reason being that we have to use random annuli in this work, and because they're independent of each other for each copy, uh, it makes the estimates a lot easier when we have to deal separately with each integral. So, as shown in EduCase, in order to show that this letter integral diverges, they split into a summation of letter integrals. And so the question became to show that the sum of letter integrals diverges, namely satisfies some large deviation estimate, and uh, that involved a wide range of techniques, decoupling and handling decoupling factors separately from handling the coupled factors. One key estimate is a linear boundary correspondence. So the dilatation of the aqueous burning over a Whitney cube can be controlled by the quasi-symmetric ratio of the map that it extends. Okay, so that's a general result, right? So we have some Whitney square Ci corresponding to some interval I, and we're looking at neighbors J1, J2 that fall within a neighborhood, a small neighborhood of this interval I. Okay, so in order to study the sum Sn that we talked about above, we end up having to estimate the dilatation, the supremum of the dilatation. So we have to estimate products of these ratios. In the 2009 work, they studied the following product. So here, eta delta k corresponds to the field U delta k dr, okay, for some sequence delta k, deterministic sequence going to 0. And so by making an appropriate choice of scales and intervals, they were able to dominate this by a product of expectations. So yeah, the main idea here is that if I give you two intervals AB and CD, and you know that C is bigger than B plus delta, then if I give you any UT delta field, then some U delta S, then these two will be independent of each other. And so when you do that for every point in that interval, you get that integrals of these fields will also be independent because they're measurable functionals. So these two measures will be independent of each other. Now, in the inverse case, that doesn't work anymore, meaning if I give you two intervals AB and CD, the corresponding intervals, the evaluated inverse over those intervals will be correlated always, regardless of how distant C and B are. So let's talk about why is that the case. So you can write down the interval QCD in terms of infimum of this shifted inverse, right? Because eta of QC, QC plus T, if you write down QCD. What do you get? You get eta of QC, QD. They cancel out, right? So you're left with eta of QD minus eta of QC. So you get D minus C. Okay. So that's the inverse of QCD. And we have that eta of QC. We have that eta is not a GMC process. So it's definitely not strong Markov. And so this guy will not be independent of QC. And so it will not be, so QCD will not be independent of the past of other points like QA, comma B. Okay. However, we can still dominate by decorrelated factors or negative correlation, as it's called. So we start with inserting the following event, which we call the gap event. The intuition being that we have eta of QC plus T, and we are comparing it to QB. And remember, right, we have the following fact that AB is independent of, so eta evaluated of this interval is independent of eta evaluated over the CD interval. When we have that B plus delta is less than C. So this is the point of view we try to follow, that we are working in the domain of GMC. So we try to see what happens if we insert the event that QC, okay, that QC is bigger than QB plus delta, and whether that will imply any decorrelation of eta QC plus T with a QB. Okay, so that was the main idea. Because as you can see, that will then tell us about QC comma D being decorrelated from QB, from this semi-group formula. Okay, now for general multi-point moments, we need an event of the following form, where um, we need them to have this kind of ordering, but multiple of them. That was a major challenge of this proving existence of this event with high probability, meaning that we start with some n intervals, say IBI, and we have to extract Cn intervals, AIK, BIK, with probability that decays exponentially, that is exponentially high. So the error decays exponentially fast. For this, we use the perspective of independence set and independence number from graph theory. So we have vertices labeled by the inverses. So Q delta 1, A1, B1, Q delta 2, A2, B2, and so on, all the way to Vn. And we say that two vertices intersect when we have the following complementary gap event. So in this case, we are asking for Q B3 plus delta 3 being bigger than Q delta 2 A2. Okay, so if this event happens, we say that V2 and V3 intersect. So the goal was to show that in this random graph, we can extract Cn many vertices that overlap with nobody else. The intuition here is simply that uh, as eta delta, so we have this eta delta case, which is the U delta K dr. We observe that as delta K goes to 0, we are just left with Lebesgue. So, and the correlation gets smaller and smaller because remember we had this uh, T minus S being less than delta K. So our objects are becoming more and more like Lebesgue and less correlated. And so the hope is that there's less and less probability that that this event happens, right? Because if this is the converged to Lebesgue, then the same is true for its inverse. So this guy also converges to Lebesgue, and so we just have to pick appropriate D and A so that this statement is false in a deterministic level. Okay, so now let's talk about uh, the moments. So even after we dominate by that product, we still have to talk about the moments of ratios. In AGKS, they used the scaling law to dominate by the ratio of the size of the intervals. Unfortunately, here there is no scaling law because the inverse does not equal to integral of something. So right away, it's unclear. I mean, we show it in our work that there is no scaling law. Um, so there is no scaling law for this. So we have to get around it uh, by, again, trying to move back to eta and using its scaling law. So that's why this is one of the longest parts in our first article, the most tricky. And we proved the following results. So uh, suppose you fix the denominator, but you have the numerator decreasing. Then for each moment p equal to 1 plus epsilon, we can find some moment 1 plus epsilon 2 so that we can control this ratio by a decreasing quantity. Okay. So this comes to be very important when we do our estimates in the letter. We also need the case when both intervals decrease at the same time. And again, for each small p1 plus epsilon, we have the following singular bound, right? So as x goes to 0, this upper bound blows up, but at least it blows up slow. So we can take this epsilon to be small at the cost of a larger constant. Uh, let me quickly explain how this implies that the dilatation is in L1. So remember we had the supremum of the dilatation being controlled by these quasi-symmetric ratios. So so we cover the interval 0, 1, 0, 2 by Whitney cubes, and we use so we use this the above estimate for p equal to 1. So in showing in studying this expectation, so we use the previous estimate over h Whitney square. So this is where we get the epsilon ratio bound. And so since this epsilon is arbitrarily small, this integral is finite. And so we get this concrete bound on the expected value of the dilatation. Now let's talk about a little bit about the moments. So when p is strictly, or when for positive moments, p greater than 0. So we use layer cake, and we see that in order to get good control of positive moments of the inverse, we need to have good control of the negative moments. So right away from here, you see that uh, since GMC has all negative moments, this implies that the inverse has all positive moments. Okay, that's a different discussion. Um, for the integral over 2 delta infinity, we can study this using a type of strong Markov delay, which we'll discuss below. And for the integral from 0 to delta, this is far more complicated because the correlation uh, starts going being less than delta, it becomes highly non-trivial. Yeah. So we talk about a little bit on the tail interval to delta infinity. So here we use the perspective of healing times. So we know that these are independent, and we have the strong Markov property. And the question is, do we have anything analogous here? Uh, it's actually quite easy to show that uh, once you add a delta buffer, then this shifted GMC by QA is independent of the law of QA. Okay. And that means that we can forget about QA altogether and just focus on uh, determinist of eta over a deterministic interval. And so going back to those moments, we can lower bound eta QA by a shifted, which is allowed since t is bigger or equal than 2 delta. And so we're left again with GMC over a deterministic interval for which the moments are already known. In the other case of uh, being very close to delta, so in this case where we're very close to delta and 0, uh, one has to use one way is to decompose. So we decompose QA so that we don't have to deal with it because it's highly non-trivial how to study this shifted GMC. And we take supremum over that. We take the supremum over that interval ik. So again, we have a shifted eta, but uh, at least it's over a deterministic interval. And now that we are dealing with the supremum, here we used more classical techniques in chaining in order to study using dyadic intervals, and so on. But yeah, this is one of the major steps that uh, impose a huge constraint on our parameter gamma. So ideally, this is one of the steps that we would like it to be replaced by something a lot more exact to avoid this huge constraint on gamma. And the constraint on gamma comes because the moment you start taking supremum, you start dealing with uh, yeah, worse estimates, union bounds, that kind of thing. So it becomes way worse. Uh, yeah, the major difficulty here is having to deal with this field, U delta QA plus S minus U delta QA. It's unclear how these fields behave with respect to one another. Okay. So yeah, let's finish up talking about one of the last parts of the article. So um, uh, in our second article, we proved existence of a Beltrami solution for the single copy first. So a lot of the first part of the article went towards that, even though it was known already from the AGKS work that H inverse gives the Beltrami gives a conformal welding solution. So that was not and Beltrami solution. So that wasn't the unknown part here. Uh, yeah, so we made a choice of random annuli that helped us obtain that this is a Beltrami solution. So we have some AIK subsequence of annuli. But now when one is working with independent copies, one has to be careful because we have annuli for each copy, and we need the overlaps to be large enough so that the Leto integral estimate that we mentioned above goes through. Okay, so for example, here one has to take the smaller part, right, like this. Fortunately, a lot of the estimates we developed for the single copy were very helpful. So we started with our two sequences that we already had from each copy, and then we first proved that uh, starting with this one copy that we can extract some of them that intersect with some copy, some annulus from the second copy. So we could have the degenerate case of uh, all of them intersecting with only one of the second copy. So that's allowed in the first step. And then in the second step, we further extracted a subsequence of one copy annuli that uniquely intersect with some two copy. Okay, so that was the main idea there. Okay, so we give our main thanks to Eros Saxman and Antti Kupinen. Eros Saxman in particular uh, posed the question to me to find the moments of the inverse, and that's how this approach started. Please also see uh, the recent work of conformal weldings with Michael Macaulay, where they proved the existence of this gluing for two independent quantum disks using a much shorter approach that builds on the random conformal weldings. Some directions are to extend all these things to the full range. It will be fascinating to see how to extend the moment estimates. Studying the critical case, so Teku has some work years ago uh, towards building that. And it will be very interesting to extend it to general logarithmic fields, uh, extend it to the parabolic case, so now something like the stochastic heat equation, and of course to higher dimensions. Okay, thank you so much.